Light is fascinating. We have a lot of light sources around us, but most of the time they create billions of light rays moving away. This is not very easy to study. So we use laser to create this clean light ray pattern. First thing you notice is that light travels in a straight line. If there is no interference, all lines are straight. But when we put different objects on their ways, we can change this pattern. So it could be like this. This is a lens, and you can see light rays, they will bend toward a point after they pass through the lens. We could have different shapes. So this is another shape, and you can see we have different pattern using this shape. We can also use mirrors. The main difference is mirrors will reflect the light. So this is one shape of the mirror, and you can see these diverging reflections. And this is another type of mirror, and you can see converging light rays. So depending on their shape, they can bend the light in different ways. In this experiment, you don't study all types. Basically, you need one lens type and one mirror. Okay, let's start with lens. We'll use this lens, which is convex lens. Okay, now let's see how this lens works. So I have light rays, 5 light rays, and I put the lens somewhere around here. It should be straight. And you can see there is a point, and all light rays will converge here. So this point is our focal point. So focal point is the point that all parallel light rays will converge. So one focal point is here, another one is the other side. So if I move this laser here and get somewhere out here, so this is another focal point this side. So basically there are 2 focal points on both sides. Focal length from the lens to this point is a constant number for each lens. It depends on design and curvature. So no matter what happens, what kind of rays you're using, you always will have a constant number for f, unless somehow you can change the lens. Okay, now let's use individual light rays to see how it works. So I will start with a parallel light ray. So incoming light ray is parallel to the main axis. This is what I mean by parallel. Parallel with respect to this main axis. This axis is just imaginary line with F. And this is incoming light. So it's a straight line because there's nothing here. It will go straight. Then we hit the lens. There is curvature, something happens inside the lens, and finally we have this bent ray. And you can see parallel ray will go through F. Okay? And it doesn't matter where this parallel ray is. So this one is hitting here. If I have another one, this one is parallel, hits the lens, then we'll go through F. If I have Another one down here. Again, if it's parallel to the main axis, we'll go through F. Okay, so it doesn't matter where they hit. If they are parallel to the main axis, they will go through F. This is our first light ray. So I can keep this note that if I have parallel on this side, it will go to F. Now let's try a different setup. Now let's try to have a light ray going through F. Let me use this one and make it simple. Now what's happening here? We have incoming light ray, and this incoming light ray is going to F. So going to F hits the lens. Then we have parallel light ray. So F parallel respect to the main axis. F on main axis. So if I have F, it will go parallel. And also doesn't matter where is the orientation. So again, if you have something around here, you see, doesn't matter. That's the rule. If hits this side, again you can see F parallel. Okay, so this orientation doesn't matter as long as you have a light ray hitting F, it will go parallel. This is the last one, and this one is kind of easy because this is center. If I can make it hitting center, that's the center. So in this case, this light ray hits the center, and you can see there is no change. Okay, so if it's center, no change. And again, doesn't matter, you can go through here. If it's center, there is no change. You can go through here. If it's center, there is no change. Okay, now let's make it more complex. So instead of one light ray, in this case, we have an object. So let's say this is an extended object, and we use arrow because we want to see what's the direction at the end. For any extended object, remember we have billions of light rays. So we have billions of lights going away, but we only know 3 rules here. So let's use these 3 rules. So first rule says, if I have a parallel ray, it will go through F. So I will pick one point here and another point here. Let's say this is point A. So for point A, this is parallel ray. So this is the main axis. I'm just drawing a line. Parallels. So this is first light ray. Parallel should go to F. So no change. We hit the lens. Then after lens should go to F. Okay, that is first light ray. Second one says F parallel. So let's draw F. Hits the lens, and this should go parallel. And that's enough for this point. Okay? So point A is here, and this is our object. And this is image. And this is the point I'm looking for. So A goes here. This is A prime. But I'm not done yet, because this is just for this point. I need a second point. For second point, I will use this end. So this is B. Again, I have parallel. And don't worry about these rays. Okay, this is parallel. What happens to parallel? Hits the lens, then it will go to F. Okay, and then I need another ray. This is F. With the lens, and this should be parallel. And this is second point. So final image is like this. So in this case, image is inverted and it's slightly smaller. You can see this is our initial size and final size is smaller. Okay, I just cleaned up all light rays, so this is easy to follow. So if you remember, we have an object here, and this is the lens. We have focal points here, and this is final image, just in random image and object. Now we are going to calculate these distances. So this distance, focal length, is f. It's the same on either side. This side or this side, it's the same. From object to the lens, we use u. And from image to the lens, we use v. Okay? So focal length, u, and v. And the relationship between these three parameters is like this. One over u plus 1 over v is equal to 1 over f. Okay? So 1 divided by the distance between the object and the lens plus 1 over the distance between the image and the lens is equal to 1 over focal length. This focal length is a constant number for this lens. One interesting case is when we put an object between focal point and the lens. Let's say this is object. And what happens in this case is interesting. I will simply draw light rays. So I have parallel the lens. So this will be f. In this case, I can't have f parallel, so I will use center no change. Okay, so this is center hits the lens, so there will be no change. And you can see we have a problem here. Okay, so I just did for 1 point, parallel f and center no change. And problem is they diverge. So you can't find any image point on this side. Okay? So there is no real image in this case because light rays diverge. What happens if we look from this side, there will be a brain game, a brain trick. So our brain will create an image. Okay, so it looks like the image on this side. So our final image will be like this. Okay, but this is not real. This kind of image is called virtual. So this image is virtual, and it's erect. Okay, everything we said so far was for lenses, but what about mirrors? If I have a mirror, what are the rules? So basically rules are the same. Let's say this is the mirror, and again for mirror we have a convergence point. All light rays, they converge here, and this point, not surprisingly, is called focal point. So it's the same idea. And again, for mirrors, if we have parallel, we'll hit the mirror, and reflection will go through F. And it doesn't matter where this parallel ray hits. Parallel F, parallel F. Or even this side. So we have parallel F. So first rule is the same, but instead of passing through lens, for mirrors we have reflection. We have reflection from mirror. Parallel, reflection towards F. And if we have a ray going through F, F is parallel, right? Okay, now let's see how a simple telescope works. So we have the first lens, which is the main lens with longer focal lengths. And then we have a smaller lens as eyepiece with shorter focal lengths. And basically what we do in telescope, using this combination, we magnify object in the sky. So final image is much larger than the main object. So what we need to know is what is the magnification. And magnification is basically focal length of the main lens divided by focal length of eyepiece. So magnification is equal to FO divided by FE. Technically, the main lens is more expensive, so we don't change the main lens. But in order to get different magnifications, we change eyepieces. So this number is a constant number, and we replace eyepiece with different focal lengths. So for example, if FO is 100 for this, so whatever unit you have, and if E is 10, basically your magnification is 100 divided by 10, which is 10. It means final image is 10 times larger than the object. So what happens if we change this number? So let's say we have 100 for FO, but we use a shorter focal length. For example, we use 5 instead of 10. So in this case, magnification is 20. So if we decrease FE, if we use shorter focal lengths, we'll have higher magnification in our telescope setup.